Okay, so we should start now. Now let us see the optimization problem. Let us see the optimization problem. I have got a function and I want to find out what is the maximum value or the minimum value of the function. Now the general thing is, if I have got a function f of x, then to find out any extremum, we can say maximum, minimum, doesn't matter. So what we do, we differentiate with respect to that and make it 0. Correspondingly, we find out, forget about that second derivative, all these things, that I am not talking about. You take a function and differentiate that particular function and find out what is the maximum value. Let us say maximum value or minimum value, right? So those type of optimization techniques which we have studied in schools, in colleges, they are called the derivative-based optimization. They are called derivative-based optimization. Derivative-based optimization. Okay. You take a differentiation, okay, a differentiation. But as I told you, derivative operator is a very serious operator which should be avoided under any circumstances. Because when you are differentiating, many cases, many functions, the differentiation doesn't exist, right? So a new class of optimization techniques were developed, and which is called derivative-free optimization techniques. Most of the bio-inspired computing in general, say genetic algorithm, particle swarm optimization, say ant colony optimization, random forest algorithms, all these things, and essentially, evolutionary competitions, essentially, if you see it, it optimizes a particular function and gives you a solution which does not require any derivative. It is a derivative coming under the framework of a derivative-free optimization. There is no derivative operator there, right? It is no derivative operator. Got a point, the concept here? We usually do the derivative, differentiate and find out, but which is not the case. GA belongs to a class of derivative-free optimization techniques, DFO methods, right? DFO methods do not require any gradient or Jacobian, no differentiation operation, suitable for discontinuous functions or noisy objective functions, complex simulation black box model. You see, discontinuous functions. What is discontinuous functions? When the functions are defined, jump discontinuity, right? Jump discontinuity here. Now this point, what is the value? It is value is +1 or value is -1. How do you know? Got a point at this point, right? Jump discontinuity, right? So GA-based methods are derivative-free optimization techniques. Do not require any gradient, right? And you can optimize certain things. Genetic algorithms, so most of the bio-inspired computing, they say it bio-inspired computing, right? Usually, bio-inspired computing, right? So this is essentially optimization algorithms. Now these things are being used in many applications, in control, in signal processing, in identification, many places these things is being used. Okay, concept is essentially optimization. Optimization. Let's see, derivative free optimization. And this is iterative. Okay, we'll see to that. So, I'll tell you when I first attended one of the talk in genetic algorithms when I was in Sheffield. This Peter Fleming, who has written that genetic algorithm toolbox for MATLAB, he has got many students. One student was presenting something. He was using some terminology, you see, genetic algorithm terminology, population, genes, chromosomes. I did not get anything out of that. What the hell is talking about? This is a control department. What is talking? Chromosomes, genes, population, crossover operator, mutation operator. What is that? You should, just like in the next lecture, I will talk about the reinforcement learning controller, agent, state, environment. What the hell is agent, state, environment? I always ask when 2018, I have got a student doing PhD from Guangzhou in China. So she was doing PhD on the reinforcement learning controller in power system. We have published papers in transactions, industrial informatics. The same thing, Joey came to me, she's a girl. Joey told me agent, environment, state. I told Joey, don't talk all these language. You make a presentation where you map it. What is the meaning of agent in control parlance? All these things, right? So similarly, initially I did not have a clue. Just like I told you, where I didn't, what problem I have faced, I'm sharing with you because I have found a solution now. Diphontine identity, I was surprised. Consider diphontine identity, where does the identity is coming? Why it is coming, that we do not know, right? So what happens? Genetic algorithm is a derivative-free optimization algorithms. So what it does, it has got some way to do it. So what I do, suppose I have got a function f of x. Say x is q plus 10x to the power 5 minus 7x to the power 9, like this. Now I want to find out I plus 10 x absolute value of x. Let us say I want to find out what the value of x, what the function has got a extremum. Minimum or maximum doesn't matter. So what I will do, I cannot use del f over del x. I cannot use, because that is x bar x. Okay? So that function differentiation doesn't exist. So what I will do, I will search. I am not solving, you see. I am not solving any gradient optimization. I will search. Okay. So I have got, let us assume, x has got some, let us take arbitrarily, randomly I will generate some values. Randomly, I will generate some values. X is equal to 1.2, 1.5, 2.4, 2.5. Just randomly, what I will do, because I cannot do these things randomly, generate some values of x. Randomly generate, right? Say for example, I'm telling x is equal to 1.2, minus 2.1, 3.5, 7.9, minus 10.2, like this. Okay? Now, what I'll do, I'll generate some random values. Each value, I will compute what is f of x. I will compute x at each value which I have generated, right? Then find out which value gives me the maximum or the minimum. Got my point? Suppose I cannot differentiate, so what I am doing, I will generate randomly. I will generate randomly, then some values, and substitute those values in the function and find out what is the value there, and then see which value gives me, let us assume the minimum value problem, let us say, for this lecture, where the fx is minimum, right? You do anything, doesn't matter. You do anything, that you generate few samples. You generate 5,000 samples. You generate 5,000 samples, any matter you generate, I am not bothered. Okay. Now suppose, because you have all your own limitations, suppose you generate some value between minus 100 to plus 100. Suppose you generate any 20,000 pairs of values between minus 100 and plus 100 and put it into x and compute x value, then find out which value of x the function is minimum, right? Now let us assume I found fx is minimum when x is equal to 91.234. Right? I found out because I calculated all 20,000, 50,000 values. Is it the true answer? That is the question. Suppose the true minimum value of x, the value of x where the function is minimum, suppose it is minimum when x is equal to minus 402.5. Suppose the function has got the minimum value, the true solution is minus 402.5. Now you have generated a random value between what and what? You will certainly get one value where the function is minimum. But that is not the actual minimum. The global minimum is lying there in minus 402. Right? Anyhow, so this is a short space. This is a short, you define a short space. You understand where I am coming from? I have got a function. I want to find the minimum value. I can do the usual way, differentiate that function, but I cannot do it because the differentiation doesn't exist, that thing. So what I do, I generated a random values between some limit and limit, and for each value, I will compute this particular function, right? Then I will certainly get a solution, no doubt about that. But is that solution true? This is not true in this case. The function has got true minimum value at minus 402, but my short space is minus 100 to plus 100, right? Okay, understand this? So we are not entering into that. So what you do here, let's come to this point first. If you are not using derivative-based optimization, you generate a set of possible solutions, minus 100 to plus 100, let us say, you generate random numbers, these are called the set of possible solutions. It may not be the solutions, set of possible solutions, right? And for each possible solution, you compute the objective function, fx, that is the function, okay? This set of possible solutions in genetic algorithm has got a name. You generate a set of population or chromosomes, each chromosome. Okay, the chromosome is one of the possible solutions, minus 2.2, minus 3.4, okay? Chromosomes. Chromosomes are a set of possible solutions. A chromosome is one of the possible solutions, and the set of chromosomes is a population. Okay? All is minus 100 to plus 100. So when the genetic algorithm first term is a chromosome, the chromosome is nothing, you see, it is a possible solution. It is a possible solution. Just like here, some number. But normally what we do, this possible solution, I'm not talking about real-time genetic algorithms, possible solution is usually binary coded. It is possible to real code, in a particle swarm we do it, but doesn't matter. Now let's say binary coded. So that number, instead of minus 2.1, it is a binary string. See here. Suppose I have got a string, a binary string. One possible solution is 1 0 1 0 1 1 0 1 1 0. So this is one of the possible solutions. Okay. So another binary string, another number. So these are the binary strings depending on number of bits. You define a range. Okay. So you generate the possible solutions. Suppose you generate the chromosome, 4-bit chromosome, binary string. So that means your possible solutions is between, forget about negative numbers, say 0 to 15. Possibility 0 to 15 or depending on negative number, doesn't matter, right? So chromosomes are the possible solutions, okay? And the solutions are actually real, no doubt about that. They are numbers, right? But we encode it as a binary string, because that we will see why you are using it binary strings. That will come later on. So GS has got chromosomes. There is a term called chromosomes. Generate a set of populations with many chromosomes. Okay. Then what you do, let's see. Is it coming? It's not moving? Yeah, moving here. First, you define a set of possible solutions. That is a chromosome. Okay? You will do it today in the assignment. Say, for example, my function is a 3-variable function. x1, x2, x3. My function is 3-variable functions. So, I don't know which value of function, it is minimum, right? So I will define a possible 3-variable chromosome. 3 chromosomes you see here. One set is, suppose 12, 6, 9. So 12, instead of 12, 6, 9, I can generate 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, right? I generate. Okay. Yeah? Here, this is one chromosome. This is one chromosome, okay? And this represents 3 number of variables. That you know, the 3 variables. Each variable has got 4 bits. Each variable is represented by 4 bits. And there are 3 variables, x1, x2, x3. And this is a chromosome, right? Similarly, I generate a set of chromosomes. That means it's a population. Not only 12, 6, 9. I generate, say, 10, minus 5, 3. This way. So this is a chromosome. Encoding schemes provide a way of translating problem-specific knowledge directly into GA framework, and thus play a key role in determining GS performance. You have to encode it. Okay. In the program, the MATLAB program is simple. You just give a random number, it will generate a random string, right? Then here, as I told you, see here, I'm explaining what the meaning of that. Let us take only one set of chromosomes, not really, because on the, you see, this is one chromosome, this is another chromosome, this is another chromosome with different bits, possible solutions, right? So 10, 11, 12, right? These chromosomes. You first generate, right? Then, suppose this is 8-bit. Each chromosome is 8-bit. It has no meaning for you. 8-bit doesn't have any meaning. That 8-bit in binary string can represent any number depending on how you interpret. Say, for example, that 8-bit between 0 to 255, or minus 127 to 128, or minus 20,000 to plus 20,000. It all the scaling factors. What happened? 8-bit, you decide that the range of the number, that you have to decide. While designing the controller, you say, my KP value should be between 0 to, say, 1 to 5, but you are representing that by 8-bit chromosome, so that means, I'm just explaining these things here. If the range of the variable, say between minus 5 to plus 10, right? That means when this is all 0, 0, 0, 0, it is minus 5, and 1, 1, 1, 1, it is plus 10. So that transformation has to be there, the range which you are giving. Otherwise, it has no meaning, right? So this one, you generate a set of chromosomes, possible solutions, and in the back of the mind, you know how to decode the chromosomes depending on the range. You generate 0, 0, 0, 0, what is 0, 0, 0, 0? 0, 0, 0 depends on what the range. You have to give the range. First generation. First you generate a set of chromosomes, then this scaling is there. Then for each chromosome, each possible solution, you find out that the FX value. You find out the FX value, just like I told you. X is equal to 10.1, 10.2 minus something. The first generation, now you find out which chromosomes has got the minimum value. Which chromosomes have minimum value? Say few chromosomes, or suppose you generate 100 chromosomes, 100 solutions, then you found, then you organize them, sort it. Which one has got minimum, next, sort it, right? So now I find out CR1, CR2, up to CR100. So this is the chromosome which is the minimum, next minimum. So what you do, you go to the next generation. First generation, first you generate and compute it. Then that is the meant to be perfect, as I told you, right? Because the solution is minus 400, but you are generating minus 100 to plus 100, clear? Because the initial chromosomes which you have given, the solution may not lie there. Solution may lie in some other places, right? So you first give those chromosomes, first generation, first you compute what is the value. The rest 98 chromosomes, you change it, a new set of solutions. First you get the solutions, which chromosomes gives the minimum value. Keep only 2 or 10, doesn't matter. That's the principle of L13, right there, but doesn't matter. Next generation, multiple generations, that is they say, multiple iterations, multiple generations. You generate a new set of possible solutions. New set of possible solutions. No. In next generation, you have to generate new. Yeah, otherwise you minus 100 plus 100, what's the point? Because it will give the same value. You generate a new set of possible generation. How to generate? There is a way to generate it. There is a crossover operation where you generate it. Now see, I'm showing you how to generate. Now see first one, this point just see here. Suppose I have got a chromosome, one possible solution is first generation, 1, 0, 0, 1, 1, 1, 1, 0, one chromosome. The second chromosome is 1, 0, 1, 1, 0, 0, 1, 0. First generation, these two chromosomes, right? In the next generation, I will generate a new set of population by using crossover operator. What I will do, the first case, I will change this part into here and this part into here. You see here? The second generation is 1, 0, 0, 1, 0, 0, 1, 0. It went to other side and that one came here. Got my point? Did you see the chromosomes difference? A new set of solutions. Or either you can do it that way, single point crossover, or more 2-point crossover. You see, one, this one. This part is changed. Other things remain same. See here. This part goes here. This part goes here. And this part come here. Other things remain same. So this is how you change the chromosomes. 2-point crossover or 3-point, new set of solutions. First you generate one set of solutions. Then after crossover operation, you generate new set of solutions. Did you get it here? This point is important. First chromosome, generation 1, the chromosome was 1, 0, 0, 1, 1, 1, 1, 0, right? In the second generation, this chromosome is not there. But there is no point. Already we have known what is its fitness value. So that is 1, 0, 0, 1, 0, 0, 1, 0. Because I change the patterns. No. See here, I'm doing it in the real domain, you can know it. Suppose the first solution, first set of solutions, possible solutions, let us say, first set of possible solution, X value is 32751 5 192467 235193, this way, first set. So for each value, I computed the value, right? These are the X1, possible solution, X1, X2, X3 in the first generation. In the second generation, what I will do, suppose I do this point, 3 to 7. Suppose I want to do this point crossover, so I will generate 3 to second 5467 and 197515. No, there is no criteria. There is a probability. You just use a high probability, so that with that probability it will change. This is randomly. Just do it randomly, right? So you see the crossover. How I do it here? You see, these things went here, and these things come here, right? So similarly, I generate a new set of chromosomes, new set of possible solutions, and each solution I have to find out what is the minimum value. Then I will get it, which one is the best. Then I will skip the first few, and the rest of the things, again the same thing. Generate a new set of population, new set of chromosomes. In this way, you continue and finally you find out a converged solution. Okay? This is a crossover operation. But sometimes what happens, you have to apply a mutation operator. That means here you see, you just arbitrarily flip one particular bit. Say 4, you make it 0. Arbitrarily. Mutation operator with a very low probability. Essentially, you generate a set of chromosomes, that is a population, then try to generate new set of chromosomes using a crossover and mutation operator. Okay? And these are all random chromosomes. And for each chromosome, you find out what is the objective function. And finally, you will find out only those chromosomes which give the minimum value, you will get it. Mutation operation, these things has to be done with some probability, not that you should do, and mutation probability is very less, just little bit, yeah. Crossover explores the current gene potentials. However, if the population does not contain all the encoded information needed to solve particular problem, no amount of gene mixing can produce satisfactory solution. A mutation operator is capable of spontaneously generating new chromosomes. Okay, so the mutation rate should be less. You see, 0.1 probability. Okay. So essentially, randomly generate a possible set of solutions. Each iterations, you generate new set of random solutions. Each iterations, you generate a new set of random chromosomes. And for each case, you compute the fitness value. Right? And while doing it, always keep the best ones to the next iterations. Always keep those things. Okay. Principle of elitism, you see here, these things I keep it. This is first generation, these are the top ones. Then I keep it here. I do not apply the selection crossover operations here. So I put it for the next generation. And in the next generation, new chromosomes will be there. So next generation, these things which are there may not be the best. A new set of things you will get the best. So those things you keep it. You just keep few. Initialize a population with randomly generated individuals. You see, this is the point where the students will get confused. They are coming to solve a control problem, a signal processing problem, or a, so we could say generate a, you see, initialize a population with randomly generated individuals. What you will say? No, that means generate a set of possible solutions. Because we are interested to find out the solutions, right? And those solutions, each solution is an individual. The entire set of pool of solutions is a population. Okay. Select 2 members from the population, 2 solutions with probabilities proportional to their fitness values, apply crossover operation, mutation operation, and do it. And repeat. Suppose you want to design a PID controller. Let us see how it will work, which you will do in the assignment. You want to find out P, Kp, Ki, and Kd. So how many variables you have to design? 3 variables. So now you define a chromosome. Suppose each variable, it is a 8-bit. You can decide any bit, 8-bit. So there are 3 variables. So how many variables, what about the chromosome length? 24-bit, clear? So you know that this particular n bit is Kp, Ki, and this Kd. You know it. That is up to you. Also, you have got a rough idea that what is the range of Kp. Because this, suppose this is a 4 bit, this is 0, suppose Kp maximum value is 10. So if this 4 bit is 1, 1, 1, 1, that means that is 10. Suppose Ki should be 0.5 maximum. So when these 4 bits are 1, 1, 1, 1, that means 0.5. Because that you decide. You decide that Kp value, maximum value is this much, minimum value is this much. That you have to mention. Because while back decoding, it will decode accordingly. Otherwise, what is the point? So Kp, Ki, Kd, chromosome is equal to controller parameters. Example, PID against Kp, Ki, Kd, represented binary settings, real valued vectors, now more efficient, but now doesn't matter. Even the particle swarm we do to real valued. Then, how to do it? You see, I will tell you. You generate a chromosome. See here. I'm just giving an example, you will find out. You generate the chromosome, and this is the Kp, Ki, and Kd, right? Now let us assume this one is 1, 1, 1, 1. This is a 0, 0, 0, 0. And let us assume this is also 1, 1, 1, 1. Let us assume. And you have given, that is up to you, that Kp is equal to 15, 25. Ki is equal to 0.1 to 0.9. And Kd is equal to 5 to 7. This is the point you have given, right? Now, first chromosome which is generated is 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. When you decode it, what is the value of Kp? Tell me. Kp is equal to 25. What is Ki? 0.1. What is Kd? 7. Because that is how you have mentioned, right? If you are given different range and this is different, it will decode different value, right? Once you know Kp, Ki, Kd, then you put it in the control algorithm there. You see, is equal to this value of Kp into Et plus Ki integration Et plus Kd, these things. You can do the simulation. Get the error. Then find the function. Which one you want to optimize? You want to optimize this error. Depending on that, which function you are optimizing, right? Now see whether that is a minimum or maximum. This is the function you are, right? See, chromosome PID against GA for PID simulate system response for each candidate. Each chromosome will give you Kp, Ki, and Kd, right? So for each one, you simulate, you find the output, then compare with the reference, find the error, first chromosome. So there are 40 chromosomes. For each 40, you find out the values. Then decide which one is minimum and the second minimum. Keep those things for the next generation. Then continue. Got my point? So finally you will find, right? So similarly, for system identification also, so theta 1, theta 2, theta 3, right? You give it. Just theta, you generate chromosomes, okay? Then for each value of theta 1, theta 2, theta 3, you decode it, then multiply it and find out the error, which one is the best. You will do it in the assignment today, you will find out how. This is very simple actually, quite straightforward. First, represent as a chromosome, then decode it back into real time, real number, put that thing in the system and do it. Okay. Similarly, particle swarm optimization, we are not talking about those things. And how the PSO work, I think Faisal was talking. This is, Faisal has done it actually. I told Faisal, you do it. See, the program is here, yes. This is the MATLAB program for a particular function minimization first. You can first check it, then other programs are also given there. So we'll take a break now. Yeah. Yeah. That's fine. No. Yeah. Yes. Yeah. Yeah. Anything. Yes, you can do it. Any questions you will do in the assignment today? I've got the program I have given you. Did you check it yesterday? Yeah, it's working now. Yeah, bit to numerator, how to convert it, chromosome, how to generate chromosomes, these things. Yeah. Which one? No, I couldn't get it. Just come here.